So our next talk is, thanks again, Alex. Our next talk
Yeah,
is going
sure.
Dan Shim from Arizona State, talking about hydrogen reaction with rocks and metals in the deep interiors of Earth and planets.
Okay, good. So thank you so much for the opportunity to introduce our recent results. And we have seen a lot of beautiful results last 2 days, and this is third day. I like to take a little different approach for the, in a discussion of future of our community today. So several presenters so far have shown this important report that lay out the community based vision of what would be an important topic to investigate in this next decade in earth science, which is Earth in Time. And this is incredibly challenging project and challenging topic, in fact, because if you go back to 4.5 billion years ago, which defines more or less the Earth's chemical structure, it's very difficult to find a record to understand. So how do we solve this very difficult problem? Well, one approach, there are many different approaches, of course. One approach that I like to discuss today is to learn about our past, important past through through understanding our neighbors in our solar system and exoplanetary systems. There are links. There are also unlikely links, but within the solar system, we already know that the Jupiter may have played an important role for shaping our planet as well. So there are also other way of linking the exoplanets and solar system planets together with Earth. So last 2 decades, we have seen impressive development in exoplanet research. Here I'm showing two properties. You can see a lot of data points there. We have about 4,000 to 6,000 exoplanets with measured property. In this slide, I'm focusing on mass, radius, and the semi-major axis, so the distance from the star. You have to be very careful when you try to interpret this type of diagram because there's an intrinsic observational bias. So for example, the planets that are very light and small is very difficult to detect, for example. So even if they are ubiquitous in the universe, we may not be able to see them yet in this diagram. Nevertheless, you can find that there are clusters of planets that exist in some parametric space, telling us something about their origin and their formation processes. And that's what I want to learn from. And before I move further, I really want to emphasize that the physics, we have provided very critical data for all your development of the exoplanet science. This is a famous example where you can see planet size on the y-axis and the planet mass at the x-axis. You can see red dots, those are exoplanet data points. There are little triangles there, the bluish turquoise color triangles that are from solar system. And then you can see those mass radius relations of different material from iron, rock, water, and hydrogen. Those are from equation of state measurements in the lab. And you extrapolate to the high pressure, and that actually provides you with a very handy tool to make an inference of composition from mass and radius relations. It's not a perfect method. We are getting better, and the astrophysicists are getting better. And I believe this approach will still remain very important, particularly in the development of detecting smaller size planet in the near future. But what I want to emphasize is that we have played an important role. And I believe that we will play a vital role in the next decades in this field as well. So a particular example that I want to discuss today is water and hydrogen. So in the solar system, we have two gas giants. Recent Juno mission have shown that this, previously believed pure hydrogen envelope is actually not pure. Well, it contains helium, that's been well known. But what was found is that the gravitational field measurements is more or less consistent if you assume large concentration of heavy elements to very shallow depth. more than 60% of the Jupiter's radius. Well, it's a very difficult challenge to explain this rather unusual compositional gradient. Well, there are many different ideas to understand, to try to explain the origin. One of them is shown here, where a large impactor collide with the core of proto-Jupiter and then disperse heavy elements into the hydrogen envelope that creates the inferred compositional gradient in the Jupiter. Well, this is certainly an attractive model, but as a chemist, we can ask question how long the structure can be sustained. To be able to answer that question, it is really necessary to know how hydrogen would interact with silicate and metals at high pressure and high temperature conditions expected for the gas giants. The compositional gradient has been actually proposed for Uranus, which is a quite different body. You have large concentration of water and you have hydrogen-rich atmosphere. In fact, Uranus is one of the mysterious objects in the solar system in terms of thermal structure, because it has extremely cold, one of the coldest atmosphere in the solar system. One explanation has been that somewhere in the Uranus interior, there might be some sort of compositional gradient that trapped the heat from escaping to the space. Although that idea has been in the literature for decades, no one actually understands exactly how the compositional gradient could be created. Here, what I mean by compositional gradient is some concentration of element heavier than hydrogen and helium. In this context, it is also important to understand, in this case, hydrogen, water reacting with silicate and metals under high pressure and high temperature conditions. These are very different conditions from the Earth interior present day, because you're talking about hydrogen saturated conditions and water saturated conditions. In exoplanet science, there are many planets now documented, as shown by this histogram between Earth and Neptune. We call them now super Earth and sub-Neptunes. Sub-Neptune so far represents the most common type of exoplanet in our galaxy. So it's an important object. To be able to understand this demographic, it is important to understand what exactly sub-Neptune is. Well, we don't know exactly what they are yet, but the most popular model to explain sub-Neptune is to have either silicate or metal or both in magma ocean under very thick hydrogen atmosphere. And the interface between hydrogen and magma ocean is about estimated to be 5 to 20 gigapascals and above 2000 Kelvin. That's pretty much within the pressure range we can comfortably approach in a laser heated diamond cell. If you go back to this histogram, you will notice a couple of very interesting, intriguing features. For example, there's a radius gap. There's a dip in between population of super Earth and sub-Neptunes. And then if you go higher size of sub-Neptunes, the population tails off. So the most popular model for radius gap is gas loss. So sub-Neptunes typically exist very close to the stars, and they probably might have lost the large amount of hydrogen atmosphere to turn them into super Earth. And in that case, it's very interesting and intriguing to think about what type of hydrogen rock interaction you used to have before you lose the gas. And some portion of them might have been sort of stored in the interior. Another interesting thing is radius cliff. It has been in some models try to explain radius cliff as a sort of hydrogen storage capacity inside of the planet changing with the size. So there's certainly an area where mineral physics could play a very important role for understanding these exoplanets. There are also very bizarre exoplanets out there called hot Neptune desert. So this green area shows sort of majority of exoplanet existing in mass radius regime. You see Uranus and Neptune there. And this size level of 40 Earth mass is about the core size of the gas giants. Yet you see this a very bizarre planet lying outside of the trend with extremely high density, with massive mass. And now this has been interpreted as sort of like a former gas giant lost large portion of its atmosphere through some process. It's called it's called remnant cores of the gas giant. So it's also very exciting to think about what would be the chemistry and physics of this planet. So two key processes that I want to use as an example today is in-gassing, out-gassing, in a very different context though. So if you think of hydrogen envelope, and then if you think about sort of some way to get rid of atmosphere, you know, when you have a situation where you have very thick hydrogen atmosphere, you will have some level of hydrogen solubility in the interior. And then there might be some dynamic process that actually store the interior to keep, you know, producing a situation to storing hydrogen and water as well. And this will certainly have a huge impact for mass radius relations. Outgassing is a very intense topic that is being discussed in astrobiology now, because, you know, some level of outgassing, different style of outgassing might actually rejuvenate the planet's atmosphere, but it might actually produce an atmosphere chemistry that could have been very different from the in-gassed species because of the internal process. So here it shows another example where internal chemistry could play a very important role for secondary atmosphere of some exoplanets. How does it relate to the rocky planets? I mean, rocky planets may start with little hydrogen, but more recent theories start showing this pebble accretion type of model where, you know, the planet can be built a lot faster. In that case, some terrestrial planets could have been built actually while hydrogen is around. And in fact, we start to see some interesting models in the literature that try to sort of incorporate that hydrogen primordial atmosphere while the terrestrial planet is being built. So this is not completely a different problem that we are talking about. This could relatively related to the rocky planets as well. So just about a couple of weeks ago, some of you probably have seen this paper already. In Science, there was a report about measurements of the size of the core in Mars through InSight mission. They found extremely large core size, so large that it doesn't require Bridgmanite layer anymore. And it's so large that the density would be very low. It's so large that much more light elements should exist there beyond the level that you can think about in cosmochemistry. This also raises an important question here, that deep in-gassing could also be very efficient for small bodies, which seems to be counterintuitive because of the small gravity. But, you know, there are more surprises we will see in the exoplanet science. So now going back to diamond anvil cell, how can we help astrophysicists, astrobiologists to understand these type of environment? So we have done some recent experiments, putting rocks, putting silicates, oxide, metals together with hydrogen, together with water under saturated conditions, conduct laser heating and measurements at synchrotron, APS. The most important challenge in heating water and hydrogen to both, 3,000, 4,000, 5,000 kelvins of melting temperature of rocks and metals is that it's very difficult to heat under those conditions. It's way more difficult than silicate heating. Well, owing to the development by Goncharov and Vitaly, Goncharov actually covers this topic quite a bit in the previous talk. The pulse heating actually allows us to heat these samples pretty robustly combined with gated X-ray diffraction. So that opens up a new opportunity for us to study a series of materials in hydrogen. So we put little piece of iron in hydrogen medium. In hydrogen ion system, it's been known that it forms readily Fe1 and H1. And the argument for H2 ion ratio of 1 or less has been that the octahedral site is the main site for hydrogen because it's large enough. Yet there is another site available for hydrogen to enter, which is tetrahedral site, which is fairly small. So it might be energetically less favorable than octahedral site. What we found when we heat over the melting temperature of iron and then quench it, at 300 K, we have very large volume, expended so much more than FEH and so much more than pure iron that we cannot actually draw that diagram, draw the equation of state in this diagram. And it shows very weird behavior when we decompress. Actually, it reduced the volume, which is a sign that the sample is losing hydrogen. And we conduct DFT and we find that the hydrogen concentration could be between 1.5 and 2, exceeding the range previously known. So iron melt could have a huge capacity for hydrogen that opens up the huge amount of hydrogen in gassing to certain type of planets. But there's a cautionary tale that we learned recently. If we put silicon, we find that the silicon limits the amount of hydrogen that can enter into the alloy. In fact, that is a very interesting factor. So if you, depends on what kind of light elements you put in the planetary interior, particularly the core, the hydrogen solubility may differ quite a bit. Now, we also heat series of oxide minerals, for example, Fe2O3, heated in hydrogen medium, we find a transformation from Fe2O3 to FeO and ultimately FeH. So hydrogen just strip off, iron from oxide and then make it iron hydride and release oxygen to the hydrogen medium. We conduct same experiment for MgFeO, and here we see essentially the same effect. Iron coming out from the oxide, turning into the iron hydride, and then we actually find MgOH2 in the cold spot, which means that water is in fact produced through this reaction and then react back with a silicate melt. And this opens up the possibility that even primordial hydrogen atmosphere could produce water-rich magma ocean. So I'm gonna skip this slide for the sake of time. We also study reaction between water and some other planetary materials. Some of the exoplanets, although very rare, appears to have silicon carbide or other carbide materials as a fundamental building block. So we decided to try to put SiC and H2O. We measure series of X-ray diffraction pattern during laser heating, and we find the formation of SiO2. And then we also find in Raman spectroscopy that the reaction produced the diamond. So if you summarize that into chemical equation, you have silicon carbide reacting with water, producing silicon dioxide, which is stishovite, and diamond and carbon and hydrogen. And this is very important because it's a hydrogen producing reaction that could ultimately influence the atmosphere composition through outgassing processes. At the shallower depth, we believe that carbon and hydrogen react to each other and form methane and then alter the chemistry of the atmosphere as well. So in this cartoon diagram, we are showing that if you have a silicon carbide planet, you somehow deliver the water from object delivered above the or beyond the ice line, and then you alter the mineralogy from the top, and that altering process start producing reducing gas and altering the chemistry through outgassing process. We also studied the olivine in water. So this is water saturated conditions. Then we conduct laser heating. We find that when we start with olivine, high temperature diffraction patterns start to show a very silicon rich minerals and very little Mg rich minerals. That was pretty puzzling. And then when we decompress from high pressure to 1 bar, we see sudden sedimentation of MgOH2, brucite. That was pretty surprising. And then we take out the sample and decide to look under the electron microscopy. You see the top-down view of the heating area. So you can see swell of the heated spot, and this is pretty bizarre shaped, we call it dome. We actually cut it through vertically using FIB, and you can see cross section there. And inside the dome, we have an empty space. And when we do EDX measurements, we find that the magnesium actually is selectively leached out from the heating center and moved to the edge. And then the center part of the heating spot was occupied by silica. What that means is that magnesium, combined with our X-ray measurements, is somehow dissolved into the water when it was heated above melting and at high pressure. And that by decompressing the sample, the solubility of Mg in water reduced, and then you actually have a sedimentation of the MgOH2, which is summarized in this reaction. So the deep oceans of water-rich exoplanet may have magnesium dissolved in the water layer in case water, H2O layer is in molten state or liquid state. This work was recently highlighted by astrophysicist, and she actually pointed out, and also it is actually written in our paper, that this Mg dissolution in water at high pressure might provide one possible mechanism to explain Uranus's magical compositional gradient that can trap the heat inside. And Nettleman actually mentioned about the link. And what captures my eyes is this is pretty important message to me, is that she said obtaining a wide range of experimental data is a key to understand observations and informing planetary interior models. I mean, this is very obvious statement for us, but hearing that from astrophysicists have a very special meaning for me, and also in very much big encouragement for us to actually go and contribute in this direction too. Now, if you look at the planned exoplanet missions, there are many interesting things to us. One of the very exciting trends that I can see from sort of recent missions and near future missions is that these space telescopes and ground-based telescopes are targeting measurements of the atmosphere of sub-Neptunes. And as I said, the sub-Neptunes may have very intense reaction relationship between hydrogen atmosphere and the interior. Then interior might have a big contribution potentially to the composition of sub-Neptune's atmosphere. So this is probably an exciting area. I'm not saying this is the only area. There might be a ton of other areas that we might contribute to, but this is one example that we can see a clear link between what we do and exoplanet development. Well, I talk a lot about exoplanets in this talk, but I also want to emphasize this important link. We don't have much record on understanding very early Earth, and the very early Earth or even proto-Earth might have an environment where hydrogen have played an important role. Well, this is not a definite statement, and based on a lot of hypotheses and unproven ideas. Nevertheless, I think what I want to emphasize is that understanding our neighbors in our solar system, in our galaxy, will ultimately also teach us how to look at our planets and understand all the history of our planets. Okay, so summary, thank you. Physics data will play an important role for advancing our knowledge on planetary formation and evolution, combined with our Earth observation, solar system missions, and exoplanetary missions. In particular, what I focus on today is hydrogen, water reacting with metals and silicates. There are other important topics we can think of. I can list few, but it could be even more. I think chemical reactions will be important. Critical zone may not exist 400 GPa, 500 GPa. Yes, I can see the critical zone at the coordinate boundary of 400 GPa and 500 GPa, but I also want to emphasize that critical zone could also exist at the shallower depth, 20 GPa, 30 GPa for very large body. So there are a range of pressures that we have to worry about for these type of things: equation of state, crystal structures, phase equilibria, and transport properties. This is only a few out of many important things that we can think of. Challenges in mineral physics. I'm going to focus on volatile rock metal reactions. How can we characterize volatile rich materials better? This is a very difficult question to me. How can we produce extreme pressure temperature conditions for volatile saturated system? What type of X-ray instrumentation is needed to accommodate the extreme conditions technique? And finally, how can we ensure phase equilibria under extreme conditions for volatile rich systems? Because so far what I've shown today rely on very fast heating. So this is a very challenging question to me. Finally, I'd like to thank, postdocs, graduate students, undergrad students in my group, former members and current members. I'd like to thank my collaborators. And I'd like to also thank Earth Science, Astrophysics, CSETI, FESD programs who provide a very generous funding to explore this area. And I also like to thank funding from Exoplanet program at NASA, Nexus program, astrobiology program from NASA for exploring this reactions. I'd like to thank Keck Foundation for hydrogen loading system. That was important. And I also like to mention our Materials of the Universe initiative at ASU that facilitate the collaboration between people like me in earth science with chemists and astrophysicists. Thank you so much for your attention.
Great talk, Dan. Thank you. I'm not seeing any hands yet. One question that I have for you, we've had some common themes here about things that are hard to measure or discrepant between different groups. And one of the approaches that some people take is to do round robin measurements. Do you think that that sort of an approach is something that we should be trying for dealing with some of these issues that we have?
Yeah, I mean, I don't exactly understand what you mean by round robin, but one can think of running this experiment in several different beamlines with slightly different time resolution techniques and different, things. And this is very fast measurements, sometimes contaminated by kinetics, sometimes dictated by equilibrium, somewhat unpredictable. So I think it's very beneficial to conduct this type of experiment in multiples of different, facilities with slightly different, but that slight difference could make a big difference in terms of heating.
Okay, now we have lots of hands, and Alex's was first. We probably just have time for one.
Go ahead, Alex.
Oh, I'm sorry, yeah. I just wanted to mention that, if I remember correctly, there was a French group, they reported FEH7, if I remember correctly.
Ooh.
So I suggest you to look at this literature more carefully.
Wow, that's very exciting. Yep.
Just make sure, I forgot, it's the top of my memory.
Yeah, so what we found exciting is that FEH3 seems to be stable at 2,000, 3,000 kelvins. I didn't show it today, but that was very surprising that such a hydrogen-rich compound can be still showing diffraction patterns at 2,000, 2,500 K. So
right, the experiments extend to 150 GPa at least. So
I'm sorry?
The experiments extends to at least 150 GPa.
Right. We didn't go that far for the heating above 2,000 Kelvin.
Thanks. Shim, I'm going to ask you if you wouldn't mind.
Oh, no, just a quick, great talk, and big questions and excellent approach. I enjoy your talks.
Thank you.
That's it. Thank you.